Hello everyone, and welcome back to MP Coding. Today, we continue our series on synchronization primitives in FreeRTOS. In the previous video, we explored different types of synchronization mechanisms with examples. Now, in this video, we're going to focus on one of the most commonly used synchronization primitives in FreeRTOS, message queues. Message queues are FIFO data buffers managed by the FreeRTOS kernel. Mainly used for communication between tasks, or from an interrupt service routine to a task, allow you to send structured data, not just a simple signal, between different parts of your application. For example, a producer task can send sensor readings to a queue, and a consumer task can retrieve those values and process them. Okay, let's look at the example. I've opened STM32 Cube IDE and, as in the previous video, I'm using the STM32 F429i discovery board. I created a new STM32 project and cleared the default pin and middleware settings so we can start from a clean state. First, I set the system clock to use the external crystal and configured the CPU to run at the maximum 180 MHz. Next, in the middleware section I enabled FreeRTOS using the CM-sys v1 wrapper. I left the FreeRTOS parameters at their default values. I configured USART1 the same way as before, and I also enabled the USART interrupt. The NVIC priority for the UART interrupt is set to 5. That works for FreeRTOS as long as you remember two important points. Lower numeric priority values mean higher hardware priority on Cortex-M, and any ISR that calls FreeRTOS APIs must have an interrupt priority that is compatible with your FreeRTOS. As before, I've hooked up the relevant GPIO pins to the logic analyzer so we can inspect signals during the demo. I also switched the RTOS tick source to a dedicated hardware timer instead of the default system tick. That helps avoid conflicts if you need system tick for other low-level features. These configuration steps were covered in previous videos, so I won't dive into every detail again here. Alright, that's the setup. Let's generate the code. Okay, in this example I'm not using the CM-sys layer, so I removed the CM-sys include and only added the headers we need for this demo. For this example I only need FreeRTOS and Queue APIs, so I included FreeRTOS.h, task.h and Queue.h. I've already written the code, so let's break it down. At the top I created 3 task handles and 1 queue handle using the FreeRTOS types. There are 3 task functions, 2 producer tasks and 1 consumer task. I also have the UART ISR function defined here. Before we go into the task functions, let's look at main. In main, I create the queue with xQCreate, passing the queue length and the size of each item. Here I used a length of 5 and the size of an int, because I'm going to pass integer values between tasks. xQCreate returns a queue handle, so I check the handle and print a result over UART. Next, I create the 3 tasks. Task 1 has the highest priority, task 2 is medium, and task 3 is the lowest. I used xTaskCreate and passed the task function, a name, stack depth, parameter, null, priority, and a pointer for the task handle. After creating the tasks, I start UART reception in interrupt mode so the ISR can receive bytes. Finally, I start the scheduler. Okay, now that the setup is done, let's walk through the task functions and see how the producers send integers to the queue and how the consumer receives them. First, let's understand what actually happens when we create a queue. In this example, I've created a queue that can hold 5 integer values. When we call xQCreate, FreeRTOS allocates a memory buffer in the heap large enough to store those 5 integers, plus the internal metadata needed to manage the queue. Now, when a task tries to send a value to the queue, that value is copied into the buffer, not just a pointer, but the actual data itself. By default, items are added to the back of the queue, but FreeRTOS also provides functions that let you insert items to the front of the queue if needed. We'll see that in action later. Let's focus on the typical case, adding data to the back of the queue. At first, the queue is empty. When the producer task sends its first value, it goes into the first position of the queue. The next value is placed right after it. In default case add a new value to back of the queue, and so on, until all 5 positions are filled. Once the queue becomes full, any producer task that tries to send another item will have to wait until there's space available, depending on the timeout value you specify when calling the queueSend function. On the other hand, the consumer task receives items from the front of the queue. When an item is successfully received, it's removed from the queue, and all the remaining items automatically move forward 1 position internally. That means a new space becomes available at the back of the queue, allowing the producer to add another item. So, in short, producers fill the queue from the back, consumers take items from the front, and FreeRTOS handles the internal data shifting automatically. Alright, let's see how this works in practice. In the task 1 producer, I've created an integer variable. This value will be sent to the consumer task through the queue. There's also a delay value of 4 seconds between each send operation. Here, the function xQSend is used to send data to the queue. If the queue has free space, the integer value will be copied into the queue's memory buffer. Let's quickly look at the function parameters. The first parameter is the handle to the queue we want to use. The second parameter is a pointer to the item we want to send. And the third parameter is the maximum time the task should wait if the queue is full. The xQSend function behaves the same as xQSendToBack, meaning it places the item at the end of the queue. There are also other related APIs like xQSendToFront, which adds an item to the front of the queue. I'm not going to go through all of them here, but you can check the FreeRTOS documentation or the header file for more details. Back to our code. In this example, I pass the queue handle, the address of the integer variable, and port max delay, meaning the task will wait indefinitely until there's space available in the queue. If the item is successfully sent, the task toggles the pin PG13 and sends a confirmation message over UART. Finally, it waits for 4 seconds before sending the next value. The second producer task works the same way, but it sends a different integer value and runs every 2 seconds. This task toggles a different pin PG14 so we can check task 1 and task 2 activity. Finally, let's look at the consumer task. The consumer continuously waits for items to arrive in the queue. It calls xQReceive, which reads and removes the next available item from the front of the queue. The third parameter, port max delay, makes the task wait indefinitely until a new item is available. If receiving fails for some reason, it prints an error message over UART. Otherwise, it toggles the pin PG11 and displays the received value. After that, it waits for 5 seconds before checking again. So overall, we have 2 producer tasks pushing integer values into the same queue at different rates, and 1 consumer task reading and processing those values. This setup demonstrates task-to-task communication in FreeRTOS using message queues. Now let's look at the UART interrupt service routine function. This function is automatically called whenever the UART receives 1 byte of data, because we've enabled UART reception in interrupt mode. Inside the callback, I've created a local integer variable name to send and set it to 123. If the received character, stored in Rx data, is the letter R, then we'll try to send this value to the front of the queue. I have explained why we need this X higher priority task woken parameter in previous videos. I will not going to explain it again here. That's all for the code. Let's build the code. Looks like we're getting some warning messages due to missing header files. Since we're using the sprintf and strlen functions, we need to include both stdio.h and string.h headers in our code. Okay, let's add them. Build it again. This time, there are no errors. Let's flash it onto the board. As before, I've opened the logic analyzer and the serial monitor. Okay, let's continue. You can see here that the first 2 producer tasks successfully sent their values to the queue. If I send R through UART before the queue is full, it can be added to the queue. After several seconds, task 2 enters a hold, blocked, state because the consumer releases a value every 5 seconds, while task 1 runs every 4 seconds. Since task 1 has a higher priority, task 2 cannot send its value to the queue. Now, even from the ISR, the value cannot be sent to the queue because the queue never becomes free. The available space is always taken by the higher priority task 1. Okay, let's analyze this in more detail. I ran the program for several seconds and captured both the logic analyzer traces and the UART output. On the screen you can see the UART log I captured while running the demo. And this is visual representation of the queue with the logic analyzer. At the very start, both producer tasks, T1 and T2, successfully send values to the queue. T1 sends the value 100, and T2 sends 202. Because the queue is FIFO, T1's 100 sits at the front and 202 is placed directly behind it. The consumer task T3 then runs and receives the item at the front of the queue, in this case 100. When the consumer removes the front item, the 202 automatically becomes the front item. Next, T2 sends 202 again. T2 runs every 2 seconds, while T1 is still waiting to send, because the T1 waits 4 seconds. Then I typed R on the UART console and send it, to trigger the ISR. The ISR places the value 123 at the front of the queue. You can see the UART confirmation, sent from ISR, which indicates the ISR successfully placed 123 at the front. Because the ISR used the send to front API, the 123 is now the next item the consumer will receive. It pushes existing items one position back internally. After that, both task 1 and task 2 send values to the queue again before the consumer task wakes up. At this point, the queue becomes completely full. Then, after about 5 seconds, the consumer task runs and removes one item from the front of the queue. As you can see, the value it receives is 123, which was inserted by the ISR to the front of the queue earlier. After a few more cycles, only task 1 is able to send data to the queue. This happens because task 1 has a higher priority and runs every 4 seconds, while the consumer runs every 5 seconds. So whenever the consumer removes one item, task 1 immediately fills that free slot before task 2 gets a chance. Even the ISR can't successfully send data anymore, because by the time the interrupt occurs, the queue is already full. Next, let's look at sending structured messages through a queue. In the previous example we sent simple integers. You can also pass whole structs through a FreeRTOS queue. Here I defined a message structure that contains a string pointer and an integer. When you create the queue, the item size must match the size of the type you want to send. Since we'll send struct message instances, when we create the queue we need to pass that struct size. Important note about stack size and pointers. I increased the task stack size when creating the tasks. There are 2 reasons you might need a larger stack. If you call functions like sprintf inside the task, those functions use stack space for temporary buffers and require extra stack. If your message struct contains pointers, like char pointers, you must be careful about where the pointed to string lives. Sending a struct that contains a pointer copies the pointer value into the queue. It does not copy the actual string data. If that string was stored in a local stack buffer that later goes out of scope, the pointer in the queue becomes invalid and leads to bugs. Okay, the task functions are the same as before. The only difference this time is that we're sending a struct message instead of a simple integer. I will upload all the materials to GitHub, so you can check out the full source code there. Since this example is just a modified version of the previous one, I won't go into the details again. The logic is the same, only now we're passing a struct through the queue. Let's run it. You can see that this works exactly the same way as the previous example. Today, we discuss message queues, one of the key synchronization primitives in FreeRTOS. In the next video, we'll explore stream buffers, another important synchronization mechanism. So stay tuned, and don't forget to like, comment, subscribe, and share. See you in the next video.